In the final decade of the 20th century, the aerial environment over the South China Sea was defined less by visible conflict than by an intricate lattice of assumptions. Assumptions about professionalism, about predictable behavior, about the resilience of machines engineered under radically different doctrines yet operating within the same physical laws. On the morning of April 1, 2001, those assumptions converged around a single aircraft type whose very existence embodied strategic confidence: the United States Navy EP-3E Aries II, a heavily modified derivative of the Lockheed P-3 Orion, designed not for combat maneuvering but for sustained, methodical intelligence collection at the edge of foreign airspace. Its presence near Hainan Island was routine in operational terms, but structurally and philosophically, it was an aircraft optimized for endurance and data fidelity, not for kinetic proximity to interceptors. The EP-3ES airframe traced its lineage to the late 1950s, when Lockheed engineers conceived the P-3 as a maritime patrol aircraft capable of remaining aloft for more than 10 hours while carrying significant sensor payloads. The design philosophy emphasized structural longevity under repeated pressurization cycles, resistance to saltwater corrosion, and predictable aerodynamic behavior across a narrow flight envelope. Its fuselage was built primarily from 2024 T3 aluminum alloy, selected for its favorable balance between tensile strength and fatigue resistance. Wing spars were over-engineered by commercial aviation standards, designed to tolerate asymmetric loading during low-altitude anti-submarine maneuvers. In its intelligence-gathering configuration, the EP-3E sacrificed almost all vestiges of aerodynamic elegance for internal volume, antenna apertures, and electronic racks. The result was a platform whose structural integrity depended on conservative margins rather than agility. This conservatism extended to its flight profile. The EP-3E typically operated at medium altitude, subsonic speeds, and shallow bank angles. Control authority was ample but deliberately damped, tuned to reduce pilot workload during long missions rather than to enable aggressive maneuvering. The aircraft's four Allison T-56A 14 turboprop engines delivered reliable thrust with minimal transient response, reinforcing the expectation that the aircraft would never be required to perform rapid evasive actions. In structural terms, the EP-3E existed in a state of managed stress. Aerodynamic loading was steady, cyclic fatigue was predictable, and the airframe's service life could be forecast with actuarial precision. Opposite this philosophy stood the Chinese J-8II interceptor, a design born of an entirely different set of priorities. Conceived during the Cold War as a high-speed, high-altitude air defense fighter, the J-8 emphasized climb rate, dash speed, and interception geometry over long-term fatigue margins. Its delta-influenced wing planform and powerful turbojet engines allowed rapid acceleration, but at the cost of reduced low-speed handling finesse. The structural architecture of the J-8 was optimized for transient aerodynamic loads rather than sustained ones. Where the EP-3E relied on thick skins and conservative stress limits, the J-8 relied on rigidity and responsiveness. Both aircraft were structurally sound within their intended envelopes. Neither was designed to share the same three-dimensional airspace at close quarters. The illusion of safety rested on the assumption that those envelopes would never meaningfully overlap. U.S. reconnaissance doctrine presumed that foreign intercepts would remain visual but non-contact, governed by tacit rules of separation and signaling. Chinese air defense doctrine, increasingly assertive at the turn of the century, treated such reconnaissance flights as persistent probes to be shadowed and, when possible, pressured. In engineering terms, this doctrinal friction manifested not as immediate structural stress, but as operational proximity. Each close pass introduced localized aerodynamic disturbances, wingtip vortices, pressure gradients, and wake turbulence effects that neither aircraft's designers had explicitly modeled for sustained interaction. On the morning of the incident, the EP-3E departed on a signals intelligence mission that, from a systems perspective, was nominal. Environmental conditions were benign. Visibility was high, convective activity minimal, and atmospheric density predictable. The aircraft cruised at approximately 22,000 feet, a regime where dynamic pressure is sufficiently low to reduce structural loads, yet high enough to ensure stable control response. Inside the fuselage, racks of electronic equipment generated heat loads managed by environmental control systems operating within specification. From a fatigue standpoint, the airframe was well within its expected life cycle. There were no precursors of material failure, no anomalies in engine vibration signatures, and no deviations in control surface response. The J-8 interceptor that approached the EP-3E did so under similarly stable environmental conditions, but its flight regime was fundamentally different. To maintain visual contact with a slower turboprop aircraft, the J-8 operated near the lower boundary of its optimal speed envelope. At these speeds, control margins narrow, and the aircraft becomes more sensitive to small disturbances. Lift coefficients increase, angle of attack rises, and the margin between controlled flight and incipient stall decreases. Structurally, the airframe remains sound, but aerodynamically, it enters a regime where pilot inputs must be precise and continuously adjusted. Repeated close-in maneuvers by interceptors impose a subtle but cumulative effect on both aircraft. Each pass generates wake turbulence that interacts with the other's lifting surfaces. For the EP-3E, whose large wings produce significant vortices, this turbulence propagates outward and downward, creating rolling moments that are normally countered by gentle aileron inputs. For a fighter flying within that wake, the induced rolling and yawing moments can be abrupt. These are not loads that threaten immediate structural failure, but they do challenge control authority, especially at low relative airspeeds. The illusion of safety persisted because previous encounters had resolved without incident. Structural margins had absorbed minor perturbations, and pilot skill had compensated for aerodynamic unpredictability. Yet from a forensic standpoint, each close approach represented an unquantified experiment. The EP-3Es design did not account for repeated near-field interactions with high-performance interceptors. The J-8's design did not account for prolonged operation in another aircraft's wake. The airspace itself became a shared system operating beyond its original design assumptions. Confidence in procedure substituted for explicit engineering safeguards. There were no physical barriers, no enforced separation minima beyond informal norms. The system relied on human judgment layered atop machines whose materials and structures were optimized for entirely different missions. Aluminum alloys, composite radomes, control linkages, and aerodynamic surfaces all performed exactly as designed within their intended parameters. The vulnerability lay not in a single component, but in the interface between two design philosophies occupying the same volume of air. By the time the Chinese interceptor closed once more on the EP-3Es left wing, the conditions for failure were already embedded in the system, not as an inevitable outcome, but as a possibility created by overlapping operational envelopes. Structural integrity, in this context, was not merely a function of material strength or fatigue resistance. It was a function of spatial tolerance and doctrinal restraint. The aircraft had been engineered to endure storms, corrosion, and decades of cyclic stress. They had not been engineered to endure each other. The architecture of confidence that governed reconnaissance operations near Hainan Island was therefore an emergent property. It arose from trust in materials, in procedures, and in the predictability of opposing forces. It assumed that aluminum skins would never be tested by foreign fuselages, that aerodynamic loading would remain within modeled limits, and that material failure would only occur as a result of long-term fatigue, not instantaneous contact. This confidence was not irrational. It was statistically justified by years of uneventful encounters. But it was also brittle, dependent on the flawless execution of human judgment under conditions that engineering had not explicitly constrained. In forensic retrospect, the first phase of the Hainan incident does not begin with impact. It begins with design choices made decades earlier, with the quiet certainty that reconnaissance aircraft and interceptors could coexist without touching. It begins with an airframe designed for patience encountering an airframe designed for urgency. The collision that would follow was not the failure of a single component, but the failure of an assumption that had never been formally tested, yet had governed thousands of hours of flight in contested airspace. As the mission progressed beyond its initial transit, the EP-3 EP-3E entered the operational state for which it had been engineered, steady-state surveillance under controlled but persistent stress. At cruise, the aircraft existed in aerodynamic equilibrium. Lift was balanced precisely against weight, thrust against drag. Control surfaces operated within narrow deflection ranges, minimizing hinge moment loads and reducing wear on actuators and linkages. From a structural perspective, the aircraft was experiencing what engineers would classify as benign loading. Low-frequency, low-amplitude stress cycles well below fatigue thresholds. This regime was intentional. The EP-3Es value derived from time on station, not from responsiveness. Its designers assumed a stable environment where forces changed slowly and predictably. Yet the environment was not static. Even in clear air, the atmosphere is a fluid medium governed by gradients in pressure, temperature, and velocity. At 22,000 feet over the South China Sea, the EP-3E was flying within a region of relatively smooth laminar flow, but its own presence altered that flow field. The aircraft's large wings generated pronounced wingtip vortices, coherent structures of rotating air that trailed aft and persisted for miles. These vortices represented concentrated energy, a byproduct of lift generation that could impose rolling moments on any aircraft entering their wake. For the EP-3E itself, these vortices were a known quantity, their effects fully accounted for in the design of the tailplane and control system. For an interceptor maneuvering in close proximity, they represented an external, unmodeled disturbance. The Chinese J-8II interceptor that joined the EP-3E on this mission was forced by geometry into an aerodynamically inefficient regime. To remain visually aligned with a turboprop aircraft cruising at roughly 300 knots true airspeed, the J-8II had to operate near its minimum practical speed. This imposed a high angle of attack, increasing induced drag and reducing excess thrust margin. Under these conditions, the aircraft's control response became nonlinear. Small stick inputs produced disproportionately large changes in attitude, while external disturbances, such as wake turbulence, had amplified effects. The J-8's flight control system, largely mechanical with limited augmentation, relied heavily on pilot anticipation and correction. The stress acting on the J-8 was therefore not structural in the classical sense. The airframe was not approaching its ultimate load limits, nor was it accumulating damaging fatigue cycles. Instead, the stress was aerodynamic and cognitive. The pilot was required to continuously counter rolling and yawing moments induced by the EP-3Es wake, while maintaining a precise relative position. Each correction altered the local flow field around the interceptor, creating transient pressure differentials across the wings and tail. These forces were modest in magnitude, but rapid in onset. They demanded constant attention. From the EP-3E cockpit, these dynamics were largely invisible. The aircraft's mass and wing area damped external perturbations, and its autopilot could absorb minor disturbances without noticeable deviation. To the crew, the interceptor's presence manifested primarily as a visual element off the wing, not as a source of aerodynamic threat. This asymmetry in perception was critical. One aircraft was operating well within its comfort zone, the other at the margins of controllability. The system as a whole was therefore unbalanced, not in structural terms, but in operational tolerance. As the J-8 executed repeated passes, closing to distances measured in meters rather than tens of meters, the interaction between the two flow fields intensified. The EP-3Es wing generated a downwash that varied with small changes in lift coefficient. Any adjustment by the EP-3E, minor heading corrections, slight altitude trims, altered the strength and orientation of its wake. These changes propagated aft and outward, intersecting the interceptor's flight path. For a fighter with limited low-speed stability margins, such variations required immediate correction. The concept of stress, in this context, extends beyond material science into systems engineering. Stress accumulated not as microscopic cracks in aluminum skins, but as narrowing margins. Margins of separation, margins of control authority, margins of human reaction time. Each close approach reduced the buffer available to absorb an unexpected perturbation. The system remained intact, but its resilience diminished incrementally. Environmental conditions played a subtle but important role. Although the weather was clear, the atmospheric density at altitude reduced control effectiveness for both aircraft. Control surfaces generate force proportional to dynamic pressure, which decreases with altitude. For the EP-3E, this reduction was inconsequential, as its large surfaces and conservative handling qualities preserved ample authority. For the J-8, already operating near the lower boundary of its speed envelope, reduced dynamic pressure further constrained its ability to counter sudden roll or yaw inputs. The aircraft was flying in a region where aerodynamic coefficients were changing rapidly with small variations in angle of attack. In such a regime, the relationship between pilot input and aircraft response is no longer linear. A correction that is appropriate one second may be excessive the next, depending on local flow conditions. This nonlinearity is a known characteristic of high-performance aircraft at low speed, but it is typically encountered during approach and landing, not during close formation flight, with a large turboprop generating significant wake turbulence. The design assumptions of the J-8 did not include prolonged exposure to another aircraft's vortex field under these conditions. Inside the EP-3E, mission systems continued to operate normally. Antennas collected signals, processors analyzed frequencies, and operators monitored displays. The aircraft's structural health monitoring systems, limited by the technology of the era, provided no indication of abnormal loading because none was occurring within the airframe itself. The stress was external, residing in the shared aerodynamic environment rather than within the EP-3E structure. This further reinforced the crew's perception of normalcy. The repeated intercepts also introduced a temporal dimension to the stress. Fatigue, in the human sense, began to accumulate for the interceptor pilot, who was required to maintain intense focus while operating at the edge of the aircraft's performance envelope. Cognitive load increased as the pilot compensated for each disturbance, anticipating the next correction. Unlike material fatigue, which accumulates predictably with each cycle, human fatigue is nonlinear and influenced by stress, vigilance, and workload. As margins narrowed, the system's dependence on flawless human performance increased. From an engineering standpoint, the situation can be described as a coupling of two subsystems with mismatched dynamic characteristics. The EP-3E was slow to respond, heavily damped, and stable. The J-8 was fast to respond, lightly damped, and conditionally stable at low speed. When coupled through proximity and wake interaction, the combined system exhibited emergent behavior that neither aircraft alone would display. Small perturbations were not dissipated uniformly. Instead, they were amplified in one subsystem while remaining nearly invisible in the other. The stress acting on the EP-3E structure was therefore indirect. Its large wing continued to generate lift, its fuselage continued to experience uniform pressure distribution, and its materials remained well within elastic limits. But by generating a wake field that imposed dynamic loads on the interceptor, the EP-3E became an active participant in a coupled aerodynamic system. The aircraft was not merely flying through air. It was shaping the air in which another aircraft struggled to remain stable. As the mission time lengthened, the probability of an adverse interaction increased, not because any single maneuver was inherently dangerous, but because the cumulative exposure to narrow margins reduced the system's overall robustness. In reliability engineering terms, the system's failure rate was not constant. It was increasing as operational stressors accumulated. No alarms sounded, no structural limits were exceeded, and no procedures were formally violated. Yet the conditions necessary for a rapid transition from controlled flight to loss of control were gradually being assembled. By the time the J-8 moved once more into close proximity with the EP-3E's left wing, the system was operating in a state of heightened sensitivity. Aerodynamic loading on the interceptor was fluctuating rapidly, control authority was constrained, and the pilot's corrective inputs were tightly coupled to unpredictable flow disturbances. The EP-3E remained structurally serene, unaware that the shared aerodynamic environment had become a critical component in the unfolding sequence. The anatomy of stress, in this case, was not written into cracked metal or overstressed spars. It was written into diminishing margins, invisible forces, and a coupled system approaching a threshold it had never been designed to cross. The transition from controlled proximity to catastrophic failure occurred within seconds, yet its mechanics were governed by processes unfolding far more rapidly than human perception could reliably resolve. In aerodynamic terms, the system crossed a stability threshold. The interceptor, positioned slightly aft and above the EP-3E left wing, entered a region where the wake-induced rolling moment exceeded the available corrective authority at its current speed and angle of attack. This was not a gradual divergence. It was a discontinuity, a sudden amplification of forces that transformed manageable disturbance into loss of control. As the J-8 encountered the EP-3E wingtip vortex, the local airflow over its left wing experienced an abrupt change in effective angle of attack. Lift on that wing decreased sharply, while the right wing continued to generate lift, producing an uncommanded roll toward the EP-3E. The pilot's instinctive corrective input, aileron and rudder applied to counter the roll, introduced additional aerodynamic complexity. At low speed, high angle of attack, and reduced dynamic pressure, the control surfaces operated near their nonlinear response region. Instead of smoothly arresting the roll, the correction moment lagged, then overshot. This oscillatory response is a known phenomenon in lightly damped systems subjected to sudden external disturbances. The aircraft did not simply roll once and recover. It entered a transient regime characterized by rapidly alternating moments. In less than a second, the interceptor's nose yawed toward the EP-3E, driven by asymmetric drag and delayed rudder effectiveness. The spatial separation between the two aircraft, already minimal, collapsed faster than either pilot could fully register. The initial point of contact occurred between the J-8's nose section and the EP-3E's left outboard wing area, near the propeller arc. From a structural perspective, this was an extreme mismatch of mass, stiffness, and velocity vectors. The interceptor's forward fuselage, reinforced to withstand high dynamic pressures during supersonic flight, presented a rigid, concentrated mass. The EP-3E's wing, though robustly built for lift generation and endurance, was not designed to absorb localized impact loads from another aircraft. The collision imparted a complex load spectrum into the EP-3E's wing structure. There was an immediate impulse load, high magnitude, extremely short duration, followed by secondary bending and torsional loads as the wing reacted to the sudden force. The aluminum skin and underlying spars responded elastically at first, but the stress concentration at the point of impact exceeded the material's yield strength. Plastic deformation occurred almost instantaneously. Rivet lines experienced shear loads beyond design limits, and the wing's leading-edge structure began to fail in a progressive manner. Simultaneously, the rotating propeller blades on the EP-3E's left inboard engine intersected with the interceptor's airframe. Propeller blades, designed to endure significant centrifugal forces and aerodynamic loading, are nonetheless vulnerable to off-axis impact. The collision introduced asymmetric forces into the propeller hub, causing immediate blade fracture and severe imbalance. This imbalance translated into violent vibratory loads transmitted through the engine mounts into the wing structure. Within fractions of a second, the engine experienced a catastrophic mechanical failure, shedding fragments outward and downward. For the EP-3E, the loss of propeller integrity and the structural damage to the wing constituted a compound failure. Lift on the damaged wing section decreased abruptly as airflow was disrupted by torn skin, deformed leading edges, and the absence of normal prop wash over the wing root. The aircraft yawed and rolled left, not because of pilot input, but because the aerodynamic symmetry of the airframe had been destroyed. Control surfaces responded, but their effectiveness was reduced by the altered flow field and the sudden loss of thrust on one side. Inside the cockpit, these events compressed into a sensory overload. The aircraft experienced a sharp lateral acceleration as asymmetric lift and thrust took effect. Warning lights illuminated as engine parameters went out of range. The noise environment changed instantly, from the steady hum of 4 turboprops to a chaotic mixture of vibration, wind noise, and alarms. From an engineering standpoint, the EP-3E had transitioned from a stable, redundant system to a degraded configuration operating on partial structural and propulsion capability. The interceptor's fate was decided even more quickly. The impact disrupted the J-8's forward fuselage and canopy area, inducing structural failure that propagated along load-bearing members. At the interceptor's speed and orientation, the loss of structural continuity led to immediate aerodynamic breakup. The aircraft's center of mass and center of pressure diverged violently, producing moments that exceeded the airframe's residual strength. The interceptor entered an unrecoverable trajectory, its structural integrity compromised beyond the possibility of controlled flight. Returning to the EP-3E, the airframe's response to damage followed the logic of load redistribution. With one propeller destroyed and wing damage localized but severe, the remaining three engines continued to produce thrust, generating additional yawing moments. The wing's primary spar, though damaged, retained partial load-carrying capability, preventing immediate wing separation. This residual strength was not an accident. It was the product of conservative design margins intended to tolerate battle damage or severe turbulence. However, those margins were never intended to absorb impact from another aircraft. The crew's immediate task was to arrest the aircraft's departure from controlled flight. Control inputs were applied to counter roll and yaw, while power on the remaining engines was adjusted to restore some measure of symmetry. The aircraft descended as lift was compromised, increasing dynamic pressure and, paradoxically, restoring some control effectiveness. This interplay between altitude, airspeed, and control authority is central to understanding why the EP-3E remained airborne. By descending, the aircraft entered denser air, increasing aerodynamic forces on intact control surfaces and allowing the pilots to re-establish a tenuous equilibrium. Structurally, the EP-3E was now operating in a damaged state characterized by redistributed stresses. Loads that would normally be shared across multiple structural members were concentrated into fewer intact paths. The risk of secondary failure increased with every maneuver. Vibratory loads from the damaged engine nacelle and wing propagated through the structure, potentially accelerating crack growth in already stressed components. Yet the airframe held, not because it was invulnerable, but because its original design philosophy had prioritized redundancy and damage tolerance. The moment of failure, therefore, cannot be reduced to a single impact. It was a cascade, initiated by aerodynamic instability, amplified by proximity, and realized through structural incompatibility. The collision itself was the visible expression of a deeper system-level breakdown. Two aircraft, each operating near the edges of their respective envelopes, became dynamically coupled in a way that eliminated the buffers normally provided by separation and speed differentials. In the seconds following impact, the EP-3E systems transitioned into a degraded but coherent state. Electrical power remained available, flight controls responded, and the fuselage pressure boundary, though stressed, remained intact. This allowed the crew to assess damage and execute emergency procedures. From a forensic perspective, this survivability underscores the difference between structural failure and structural compromise. The airframe did not fail completely. It failed partially, retaining enough integrity to permit continued flight. The interceptor, by contrast, experienced a catastrophic loss of structural integrity. Its design, optimized for performance rather than damage tolerance, offered little redundancy once primary load paths were disrupted. The rapid disintegration was not a reflection of poor engineering, but of engineering choices aligned with a different mission profile. High-performance fighters trade damage tolerance for agility and speed. In this context, that trade-off proved fatal. The frame-by-frame reconstruction of the collision reveals a sequence governed by milliseconds and meters. Aerodynamic disturbance led to loss of control margin. Loss of control margin led to physical contact. Physical contact introduced loads far beyond design assumptions, producing immediate material failure in critical components. Each step followed logically from the one before it, with no opportunity for human intervention to reverse the process once it had begun. From the perspective of materials science, the aluminum alloys, composite components, and steel fittings behaved as expected under extreme loading. They deformed, fractured, and redistributed stress according to their properties. There was no anomalous material behavior, no hidden defect that precipitated failure. The catastrophe was not rooted in microscopic cracks or manufacturing flaws. It was rooted in macroscopic interaction between two machines occupying the same space under incompatible conditions. The moment of failure, then, stands as a boundary event. On one side lies a system operating under assumptions of separation and control. On the other lies a system governed by damage control, emergency response, and geopolitical consequence. The transition between these states occurred too quickly for conscious decision-making to alter. It was the inevitable outcome of a coupled aerodynamic system pushed beyond its stability limits, where structural integrity was tested not by fatigue or corrosion, but by instantaneous, unanticipated contact. The aftermath of the collision unfolded along two parallel investigative trajectories, each shaped by institutional doctrine, jurisdictional limits, and the physical realities of the damaged aircraft and lost interceptor. Forensic analysis began not with laboratory instruments, but with the immediate stabilization of the surviving system. The EP-3E, having landed on Chinese territory, became both an object of engineering scrutiny and a strategic artifact. Its damaged structure preserved the physical record of forces applied during the collision, a record that investigators would later interrogate for sequence, magnitude, and causality. Initial assessment focused on gross structural damage. The left wing exhibited localized deformation consistent with high-energy impact, crushed leading-edge sections, torn aluminum skin, and fractured fasteners along rivet lines. These features were not random. Their orientation and deformation patterns indicated a force vector originating from forward and slightly above the wing plane, consistent with contact from the interceptor's nose section. Metallurgical inspection revealed ductile tearing rather than brittle fracture, confirming that the aluminum alloy had yielded plastically under overload rather than failing due to pre-existing fatigue or corrosion. This distinction was critical. It established that the wing had not been structurally compromised prior to impact. The damaged propeller assembly provided an even clearer forensic signature. Blade fragments recovered from the vicinity of the aircraft showed torsional shear and leading-edge gouging, indicative of off-axis impact rather than overspeed or material defect. The fracture surfaces displayed characteristic dimpling associated with high strain rate failure. Engine mounts exhibited elongation of bolt holes and deformation of supporting structure, evidence of intense vibratory loads transmitted after blade loss. These findings aligned with a scenario in which the propeller was struck externally, producing instantaneous imbalance and subsequent mechanical destruction. Investigators paid particular attention to the wing's primary spar, the critical load-bearing element responsible for maintaining structural continuity. Non-destructive testing techniques, including ultrasonic inspection and radiography, revealed localized cracking and permanent deformation near the impact zone, but no complete severance. The spar's residual integrity explained why the wing did not detach in flight. From an engineering perspective, this outcome validated the damage-tolerant philosophy embedded in the P-3 family's design. Redundant load paths and conservative stress limits allowed the structure to absorb extraordinary loads without total collapse. The cockpit and forward fuselage were examined for signs of pressurization failure or secondary impact damage. Despite significant vibration and shock loading, the pressure vessel remained intact. Fastener rows around fuselage penetrations showed no evidence of progressive tearing, and seals maintained continuity. This finding underscored the difference between localized structural failure and systemic airframe failure. The EP-3E had suffered severe but compartmentalized damage, preserving the integrity of critical volumes. Parallel to physical examination, investigators reconstructed the flight dynamics using available data. The EP-3E's flight data recorder, though limited compared to modern systems, provided time histories of airspeed, altitude, control inputs, and engine parameters. Analysis revealed a sudden asymmetry in thrust and roll rate coincident with the moment of impact, followed by aggressive corrective inputs. There were no indications of abnormal maneuvering prior to the collision. Control inputs were minimal and consistent with steady flight, supporting the conclusion that the EP-3E did not initiate abrupt maneuvers that could have precipitated contact. The interceptor's wreckage, recovered from the sea, presented a different forensic challenge. Fragmentation patterns indicated catastrophic breakup rather than controlled descent. Structural members exhibited overload failure, with fracture orientations consistent with bending and torsion beyond ultimate limits. There was no evidence of pre-impact mechanical failure. The aircraft's destruction was a consequence, not a cause, of the collision. This distinction was essential in attributing causality within the coupled system. Institutional analysis proceeded within the frameworks of the respective organizations involved. The United States Navy, in coordination with National Transportation Safety Board advisors, conducted an engineering-focused review emphasizing material behavior, aerodynamic interaction, and procedural compliance. The investigation treated the incident as an operational mishap rather than an accident in the civil aviation sense, yet the analytical tools remained rooted in accident investigation methodology. The emphasis was on understanding how design assumptions and operational practices interacted to produce an unanticipated outcome. Chinese authorities conducted their own examination under military auspices, focusing on air defense procedures and interceptor operations. While access to their findings was limited, available information indicated recognition of the interceptor's loss of control prior to impact. The absence of evidence pointing to structural or mechanical failure in the interceptor reinforced the aerodynamic instability hypothesis. Both investigative paths, though politically constrained, converged on the same technical conclusion. The collision resulted from close proximity maneuvering within a coupled aerodynamic environment, not from latent defects or intentional ramming. Laboratory analysis of recovered materials further refined the timeline. Scanning electron microscopy of fracture surfaces on the EP-3E wing skin showed no fatigue striations, confirming that crack initiation occurred at the moment of impact. Chemical analysis of alloys matched specification, ruling out material substitution or degradation. These findings eliminated entire classes of potential failure modes, narrowing causality to external loading alone. Human factors analysis, while secondary to material investigation, provided context for the mechanical sequence. The interceptor pilot's task environment was reconstructed using performance envelopes and simulated wake interactions. Modeling demonstrated that at the speeds required to remain alongside the EP-3E, the J-8 stability margins were minimal. Wake-induced roll moments of relatively small magnitude could exceed available corrective authority, particularly if compounded by pilot-induced oscillation. This analysis did not assign fault in a moral sense. It quantified the physical limits within which human performance was expected to operate. The EP-3E cruise actions after impact were similarly analyzed. Control strategies, power adjustments, and descent profile were evaluated against aircraft performance data. The conclusion was unequivocal. The crew operated the damaged aircraft within its remaining capabilities, exploiting increased air density at lower altitude to regain control authority. Their success did not alter the mechanical facts of the collision, but it demonstrated how design redundancy and informed pilot response can arrest the progression from structural compromise to total loss. From a forensic standpoint, the investigation's most significant outcome was the identification of a systemic vulnerability rather than a component failure. No single part failed prematurely. No maintenance error, manufacturing defect, or material anomaly initiated the event. The failure resided in the interaction between two aircraft operating under incompatible assumptions about proximity and stability. The airframes behaved exactly as engineered when subjected to forces far outside their design context. The wreckage told a coherent story. Deformation patterns aligned with aerodynamic models. Fracture modes matched overload scenarios. Data traces corresponded to the physical damage observed. There were no contradictions requiring speculative explanation. In this sense, the forensic aftermath was unusually clean. The complexity lay not in deciphering ambiguous evidence, but in accepting that the system failed because it had never been explicitly designed to prevent this class of interaction. The investigation closed with a recognition that traditional accident categories were insufficient to describe the event. It was not a midair collision born of navigational error or loss of situational awareness in controlled airspace. It was a contact event arising from deliberate proximity under contested operational conditions. The forensic record did not support narratives of recklessness or structural inadequacy. It supported a conclusion rooted in systems engineering. When margins are eroded incrementally and reliance on human precision becomes absolute, failure can occur without warning. In the quiet language of engineering reports, the incident was reduced to load vectors, stress exceedances, and control authority limits. Yet beneath that language lay a stark lesson. The physical evidence demonstrated that the cost of operating at the edge of design assumptions is not paid gradually. It is paid instantaneously when forces align in a way that materials and procedures were never meant to endure. The legacy of the Hainan Island collision did not manifest as a single technical modification or procedural amendment. It unfolded instead as a gradual recalibration of how military aviation systems conceptualize proximity, margin, and responsibility within contested airspace. From an engineering perspective, the incident forced a reassessment of assumptions that had long existed outside formal design requirements. Aircraft had been engineered to survive weather, fatigue cycles, corrosion, and even limited battle damage. They had not been engineered to coexist dynamically at minimal separation with platforms optimized under opposing aerodynamic doctrines. In the months following the event, operational analysis focused on redefining separation as a structural variable rather than a purely tactical one. Previously, distance between aircraft had been treated as a function of intent and professionalism. After Hainan, it was reframed as a load management parameter. Proximity was recognized as a mechanism by which aerodynamic forces could be transmitted indirectly, coupling two independent systems into a single unstable one. This reframing shifted responsibility away from individual pilots and toward systemic safeguards. From a design standpoint, the EP-3E itself required no immediate structural modification. Its airframe had performed within the bounds of its damage-tolerant philosophy. The aircraft survived because its designers had accepted weight penalties in exchange for redundancy and residual strength. However, survivability did not equate to invulnerability. Engineering reviews emphasized that survival was contingent on factors outside design intent, such as altitude loss to regain control authority and the absence of secondary failures in critical load paths. The aircraft had endured not because it was designed for collision, but because conservative margins delayed total failure long enough for corrective action. The more profound changes occurred in operational envelopes. Reconnaissance mission profiles were adjusted to reduce opportunities for prolonged close-in intercepts. Altitude bands, lateral offsets, and maneuvering restrictions were formalized to increase the spatial buffer between platforms. These changes were not framed as concessions, but as engineering controls, administrative barriers introduced to compensate for the absence of physical ones. In effect, procedure became a surrogate for structural modification. On the interceptor side, the incident accelerated internal evaluations of low-speed handling characteristics during shadowing operations. While no public redesign of the J-8 resulted directly from the collision, the broader lesson influenced subsequent interceptor development. Later generation aircraft incorporated improved flight control augmentation, expanding stability margins in regimes previously dependent on pilot skill alone. This was not a repudiation of high-performance design, but an acknowledgement that operational reality had expanded beyond original assumptions. At the doctrinal level, the event contributed to the codification of intercept behavior standards. Though often discussed in diplomatic language, these standards were grounded in engineering logic. By limiting closure rates, approach angles, and dwell time in another aircraft's wake, they sought to reduce the probability of entering nonlinear aerodynamic regimes. The emphasis was not on eliminating intercepts, but on bounding them within regions of predictable response. The incident also influenced how investigations of military aviation events were framed. Rather than focusing exclusively on fault attribution, subsequent analyses increasingly emphasized system coupling and emergent behavior. This shift aligned military accident investigation more closely with modern systems engineering, where failures are understood as properties of interactions rather than isolated component breakdowns. The Hainan collision became a reference case in discussions of how technically sound systems can fail catastrophically when combined under unanticipated conditions. From a materials science perspective, the findings reinforced confidence in established fatigue and damage tolerance models. Aluminum alloys behaved predictably under overload. Composite elements failed within expected modes. There was no impetus for wholesale material substitution. Instead, attention turned to how materials are stressed not only by direct loads, but by the operational context that generate them. Material failure, in this sense, was reframed as an outcome rather than a cause. The human element, often overemphasized in public narratives, was treated more clinically in post-event analysis. Pilots on both sides were operating within the constraints imposed by their machines and their missions. The interceptor pilot's loss of control was not evidence of inadequate skill, but of operating in a regime where stability margins were insufficient to absorb external disturbances. The EP-3E crew's successful recovery was not proof of exceptional heroism alone, but of an airframe that preserved controllability despite severe asymmetric damage. Human performance mattered, but it was bounded by physics. The philosophical reflection that emerged from the event was therefore not about blame, but about cost. Progress in aviation has always been measured in expanded capability, longer endurance, higher speed, greater sensor reach. Each expansion carries implicit assumptions about how systems will be used and against whom. The Hainan collision exposed the cost of leaving those assumptions unexamined. When opposing systems evolve independently, optimized for different objectives, their interaction can produce failure modes that exist in neither system alone. In the years that followed, this insight resonated beyond reconnaissance operations. Unmanned systems, space operations, and cyber-physical interfaces all grappled with similar questions of proximity and coupling. The lesson generalized readily. When systems share an environment, their design boundaries overlap whether acknowledged or not. Safety, therefore, cannot be guaranteed solely by internal robustness. It must be supported by explicit management of interactions. The EP-3E incident stands as a case study in the limits of implicit trust. Trust in professionalism, trust in precedent, trust that what has not failed before will not fail now. Engineering history repeatedly demonstrates that such trust is fragile when not underwritten by analysis. The collision did not require extraordinary error or malice. It required only the convergence of narrow margins and unmodeled forces. In technical terms, the event reshaped how margin is defined. Margin is no longer solely the difference between applied load and ultimate strength, or between operating stress and fatigue limit. It is also the distance between platforms, the time available for correction, and the stability of the coupled system. These variables are less tangible than material properties, but no less real. The cost of progress, as revealed by Hainan, was paid in the loss of an aircraft and a pilot, and in the exposure of vulnerabilities that had been masked by routine. The response to that cost was not to retreat from reconnaissance or interception, but to integrate engineering realism into operational doctrine. By acknowledging that machines impose constraints as immutable as political boundaries, aviation systems moved incrementally toward a more resilient equilibrium. In the end, the legacy of the collision is embedded not in a single report or policy change, but in a shift of perspective. Aviation safety, even in military contexts, is not a static achievement secured by strong materials and skilled operators. It is a dynamic condition maintained by continuously aligning design intent with operational reality. The Hainan Island collision serves as a reminder that when that alignment slips, failure does not announce itself gradually. It arrives abruptly, carried on invisible forces, and leaves behind only the evidence that physics was obeyed at every step.